What's the definition of binary search trees? We start with a binary tree first. So let's start with the ordinary binary tree. Then we put a binary search tree property on it. Then it becomes a binary search tree. So what's that binary search tree property? Look at this. Our goal, make this binary search trees support efficient search operation, key-based search operation, comparison, key-based search operation, binary search. So basically, we can use binary search as an example. So the binary search tree property is as simple as this. Look at this typical structure of in a binary search tree. We have a parent node X, two child nodes Y and Z. Then their keys should satisfy this property. Y.key, key of the Y node, less than or equal to X.key, and less than Z.key. That's simple. So this is the, binary search tree property. If your binary tree, the nodes stored in your binary tree satisfy this condition, then you have a binary search tree. Next question. How to print out all the keys in sorted order? Yeah, so the first application of this property, we can print out all the keys in ascending order easily. Yeah, so look at this. We do traversal, binary tree traversal. Okay? This time, look at the in order, pre-order, post-order, which way is the best. This time, you have a chance to choose the best traversal method. In order is the best. In order walk. All right. So if the current node is not null, then you process all the nodes at the left subtree, because all the keys in left subtree should be less than or equal to the current key at the current node. So that's why you complete processing all the nodes in the left subtree. Then you print the current key. Okay? Then go to the right subtree. Then you get, all the keys in ascending order. Yeah. So very simple application. Yeah. Next, search performance of BST. How fast? Because this data structure, BST, binary search tree, supports search operation. Yeah. The general binary search may not support search operation, but this one supports. So we want to look at it, the performance of the search operation. All right. Assume the height of this BST is h. Okay, yeah, height. Now let's look at the worst case, the best case. First, the worst case. The worst case, we know, if our binary search tree, like this kind of structure, okay, in this extreme unbalanced structure, this is a legal binary tree, right? Legal, okay? Then the height h, so when you do the search, you need, go h steps, okay? Yeah, jump h steps, okay? So this is the efficiency function, big O of h. what is the best case efficiency? Yeah, the worst case, easy, but what is the best case? Yeah, we want to see that best case. In order to look at the best case, yeah, let's assume we have n nodes total. Yeah, the best case here, based on the balancing principle we learned before, we try to distribute these n nodes in a balanced way, in the most balanced way. Then we get a best case. Yeah, that's simple. All right. But when we consider the most balanced arrangement, no matter how we do, we always have this inequality. So remember the, in the part 8.1, when we look at the number of leaves, look at that, number of leaves. Actually, in the, so I give you the formula here, but at the bottom, I will derive it in a faster way. Yeah. All right, so we have this formula. This formula tells us the best case efficiency is this one, log of n. That corresponds to the most balanced BST. So the worst case, the best case. So you can see the difference. Yeah. All right. Next. Yeah. I already explained, that skewed way, right? So, yeah, skewed way like that. All right. Next, I want to explain this formula. How to get that. Yeah. Pretty easy. Yeah. First, we know L less than or equal to 2 to the h. This is true for any binary tree, arbitrary binary tree, no matter skewed, balanced, full or general, we always have this formula, inequality. Yeah. Then, remember, this one, this, because this is for full binary tree. Yeah, this formula is for full binary tree. 2L minus 1. 2L minus 1. Right. But we can get things like this. All right. So because L less than or equal to that, that means the maximum L cannot be greater than that. Okay? The maximum number of internal node, plus 1 less than or equal to 2 to the h. Okay? Yeah. Yeah. Right. Yeah, because when n equals 2L minus 1, here we consider the full case. We consider the full case. Okay? Yeah. If it's not full, we can add more leaf nodes to make it full. How about that? Suppose we get a general binary tree. It's not full. Can we add more leaves to make it full? Yes. So here, because when we add more leaves, we make it full, then we have this formula, right? But that is still less than or equal to this number. Okay? Yeah. And we can write this. Yeah. Inequality, right? We can make this inequality because you add more leaves. Inequality. Okay? Yeah. So then you have that. Then you have this formula. Then you take log base to both sides. Yeah. But here we can get a simplification. This is a simplified version of that one because we use this formula. Okay? Remember the seeding function. This can be simplified as this one. So finally, we have this formula. Yeah. So this is the final version of the height for a binary tree. not necessarily binary search tree. Because when we estimate height, nothing to do with the search property, right? When we look at the height property, nothing to do with the search property. So that's why even if it's a BST or not, we always have this inequality. All right. Binary search tree operations. Now we need to do operations because we need to modify. Remember, we will use binary search tree to store dynamic data. Dynamic data. Okay? So that means the data comes in, frequently, come and go, So we need to maintain all different operations when data comes in or get out or, remove, delete. We need to have all the basic operations. All right. From a binary tree to a binary tree, so look at the operations, basic operations. First, from a binary tree to a binary search tree. So here, right, when we start, we have a binary tree, right? Then when something happens, we need to do something, but when you do something, you may change the structure slightly. If it is not a binary tree anymore, you need to recover it. So that's why we have this from a binary tree to a binary search tree, from binary to from a binary tree, binary search tree, right? Because when we start, we have a binary search tree. Okay? After we do some operations, we need to have a binary search tree. So, that's why we have these basic operations. First, insertion. So then the search operation. Given a key, we want to find a node containing this key in the BST. Deletion, sometimes we need to delete a node containing a given key. Traverse. All right, the traverse, we did that in the last part. Now let's do the insertion first. For the insertion, there is a simple recursion way to do it. Okay, all right. Suppose this is the root node of the current subtree, because we want to apply this insert function anywhere in the tree, on any node in the tree, with that node as the root of a subtree. So we treat this node as a root node of one subtree. The new node, now you have a key. So new node contains certain key. Now you do the insertion. First, if the root is empty, this is empty, the current root is empty, you just assign a new node to the current node. That's the insertion. That's the final insertion occurs. Else if, all right, so not null pointer, there is data in that subtree, so then you need to compare the key with the key in the current node. If it is less than, so you do the insertion to its left subtree. If greater than the, else, the other way, so you go to the right subtree. That simple. Okay, so that's the insertion. Search a key and destroy. Two operations. Let's look at a search first. Search, pretty straightforward. Given a key as an integer, we consider a special case. All right. So you start from the root. Start from the root. Right? Then you do a while loop. First, you compare the given key with the value in the current node. If they are equal, you'll find it, right? You return the value. If not equal, less than, you'll go to the left subtree to do the recursion, right? Because it's a while loop. Oh, this time, good. This time it's not recursion. It's a while loop. We go to the left subtree, but keep iterations inside this while loop. In this way, we can avoid recursion. So we know the recursion, if we can avoid it, we should use iterations to replace the recursion. So then, the other case, we go to the right and do iterations. So that's the search. Destroy subtree. Sometimes we need to destroy one subtree. We can do this. We start from the current node. The current node as the root of the subtree. All right. To destroy the whole subtree, we need to remove all the nodes in this subtree. Okay? We go to the left and we destroy the whole subtree that corresponds to using the left child as the root. Okay? Else, so here it means the left node is not empty, right? If it's not empty, then you destroy the whole left subtree. Recursion, using the recursion. Else if, that means if it's empty, then you look at right subtree, empty or not. If it's not empty, you destroy the right subtree. Okay? Finally, after you finish that, at the end, you destroy the current node, the root node of the current subtree. That's the destroy operation. Okay? All right. Then, next operation, deletion. Deletion is not destroy the whole subtree, only destroy one node. So this one is a little harder than destroy the whole subtree. Whole subtree, because you don't need to consider the structure thing, right? You need to fix something. No, you just destroy the whole subtree. But deleting a node, you may break the binary search tree structure. So you need to fix, you need to consider, still you maintain the binary search tree structure. So you don't want to change that. So that's why it is a little harder. So now, first, we remove a node that contains a given key. That's the general step. So we call delete node function starting from the root. So we do the search starting from the root. Then we write this delete node function, okay, using recursion to do it. Suppose this is the root node of the current subtree. So we start from there. Then we check the value. If the given key is less than the value of the root node, we should do the deletion operation in its left subtree. So we call it recursively. So go to the left subtree, do recursion. Else if greater than, we go to the right subtree and do recursion. Okay? All right, so finally, not left, not right, the given key equals the value of the current node. We just make deletion operation in the current node. But we need to write this function, another function. How to write this function? That's the key step. Yeah. So the next slide, I show you how to write that make deletion function. Yeah. All right. First case, the simple one. Suppose we have this binary search tree. Okay. All right. Now assume we want to delete this node. But when we delete this node, there is a special property. The right subtree point to a leaf. Right subtree points to a leaf. That makes it easy for deletion. Okay. So when we have this structure, the deletion is as simple as this. Okay. So you change the link from root, pass it to next one, then drop this node, and you do not need to worry about this link because there is no data associated with this link. So you do not need to reassign this link. Yeah. Yeah. So this is the simple case. Yeah. But if this link points to some non-leaf node, then you need to change this link to a different location. Yeah. So let's see the second case. This time, look at this node we want to delete. Not a leaf, right? Not a leaf. This time, you need to, after you do the deletion, you need to do a little more work. Okay. Now, we change the link point to this node. Yeah. But how about that, right? So you need to fix the relationship. Okay. Now, look at this link. We want to, if this link is a leaf, two possibilities. The first case is a leaf. Then it's easy. You just change that link to point to its left sibling, right? Yeah, that's easy. Yeah. But the question is, this may not be a leaf. This node may not be a leaf. Okay? If it is not a leaf, do recursion all the way to the left to get a leaf. You can do recursion, okay? Yeah. Because binary search tree, you can, go to the left. Always go to the left, right? Yeah. Until you get a leaf. Eventually, you will get a leaf. After you get that leaf, you point that leaf, change the pointer, point to this one. So then you make the deletion for this case. All right. So here you can see, although it is a little more complicated, for a data structure like this, we need to do a lot more operations to maintain the data structure. Because this data structure is very special. Yeah. It has special property. In order to have that special property, we need to pay the cost to maintain that data structure. So that's why we do so much work. Yeah. All right, so we finish part 2. Next, we will use BST in many different situations. All right.